Rust ownership can feel impossible when the compiler keeps rejecting code that looks correct. In this video, we will go through 25 real mistakes beginners make with ownership, borrowing moves and references. For every bug, you will see the broken code, why it fails, and the fixed version. In this section, we will look at the first ownership mistakes beginners hit in Rust. The goal is to see exactly when a value moves, why the compiler stops us, and how to choose between borrowing and cloning. This shows up all the time when a value is passed from one variable to another, and we still try to use the old name here. We create a string, assign it to B, and then print both names. Now we run it and let the compiler show us what happened. Let's break down the error. String owns heap memory, so Rust does not silently copy it during assignment. The name B becomes the owner, and A is invalid from that point forward. Now we fix it by borrowing the string instead of moving it. B becomes a reference to A, so the original owner stays alive. Now we run the fixed code and both prints work. The best practice here is to borrow when you only need read access, because it avoids unnecessary allocation. Use clone only when you really need two independent owned strings. This is a common logging example. We send a username to a helper function and then want to keep using it. The helper takes string, which means it owns the value. Now we run it and see why the later print fails. Let's unpack this. A parameter typed as string means the function receives ownership, not just a view of the text. After the call, the caller no longer owns username, so the second print is rejected. Now we change the function to accept str, because logging only needs to read the text. At the call site, we pass a reference to the username. Now we run it again, and the original string is still usable. The best practice is to design functions around what they actually need. If a function only reads text, accept close_tr. If it must store or transform the value permanently, then owning a string may be correct. This example compares two assignments that look similar but behave differently. Integers are small copy values, while string owns heap memory. Let's run the mixed example and see where Rust draws the line. Let's compare the two parts. Score is an I32, and integers implement copy so both names can be used. Label is a string, so assignment transfers ownership instead of duplicating the heap allocation. Now we keep the integer assignment as it is and fix the string part by borrowing. The reference lets us display the same text without creating a second owner. Now we run it and both sections print successfully. The best practice is to pause before assuming assignment means copy. For owned containers like string, vec, and hashmap, use references for reading and use clone only when a real duplicate is needed. Now we move from ownership moves to lifetime mistakes. These examples show how Rust prevents references from pointing at data that has already disappeared. This helper builds a message inside the function and tries to return stray. That looks convenient, but the string lives only inside the function body. Now we run it, and Rust blocks the dangling ref. Let's break this down. Message is destroyed when build message returns. If Rust allowed this reference, main would hold a pointer to data that no longer exists. Now we fix it by returning the owned string. Ownership moves out of the function and into main, so the data stays alive. Now we run the corrected version and the message prints normally. The best practice is to return owned data when the function creates that data. Return references when the data comes from outside the function and clearly lives long enough. This happens when we format a string and immediately borrow a string slice from it. The code looks short, but the formatted string is only temporary. Now we run it and see the lifetime error. Let's look at the lifetime format. Returns a new owned string, but because we do not store it, Rust drops it at the end of the line. The MSG reference would point to that dropped string. Now we fix it by binding the formatted string to MSG first. After that, we can borrow a string slice from a value that actually lives long enough. Now we run it and the formatted message prints. The best practice is to give important temporary results a real binding before borrowing from them. This keeps the owner alive and makes the lifetime obvious to both Rust and the reader. In this section, we focus on the rules that make Rust references safe. The goal is to see the compiler errors in realistic code, then fix them with smaller borrow scopes and clearer mutation. Imagine we are reading the first item from a shopping list and then adding one more item before printing it. This looks harmless, so let's write the reference first, then push into the vector, and now we run it to see what Rust says. Let's break down the error. The variable first is an immutable reference into the vector, and Rust keeps that borrow active until the final print. A push may reallocate the vector, so Rust blocks the mutation while the reference is still alive. Now we fix it by using the reference before changing the vector. The important part is that first is printed before the push, so its borrow ends naturally. Now we run the corrected version and the program works. The best habit here is to keep reference lifetimes short. Use the borrowed value, then mutate the collection afterward. If you really need the value later, clone just that value instead of holding a reference across the mutation. Here we model an account balance where one part of the code handles a deposit and another handles a fee. The mistake is creating two mutable references to the same balance at the same time. Let's run this and look at the compiler's response. Rust allows many readers or one writer, but not multiple writers to the same value at the same time. The first mutable reference is still active when we create the second one. That is why the compiler points to both borrows. Now we fix it by making each mutable borrow short. The deposit reference finishes before the fee reference starts. When we run it, both updates happen in a clear order. The best approach is to design mutation as a sequence of clear, exclusive operations. If one function needs to update a value, let that update finish before another mutable access starts. This keeps ownership simple and avoids aliasing bugs. A common real-world case is building a list of command line options before launching a tool. We own the vector, but we forgot to make the binding mutable. Let's run it and see why Rust refuses the push. Let's separate two ideas. The function owns the vector, but the name options is immutable unless we write mut. Since push needs to change the vector, Rust asks us to make the binding mutable. Now we fix the binding by adding mut. Nothing else needs to change because the vector already belongs to this function. Now we run the corrected version and the options print as expected. The best practice is to add mut only where the value actually changes. This keeps the rest of the code easier to reason about. When you see mut, you know that binding is expected to be modified. Now we move from simple references to loops. Iteration is one of the first places beginners accidentally move a collection when they only meant to read it. Here we have a simple task list, and after printing every task, we want to print the total count. The loop looks normal, but it takes ownership of the vector. Let's run it and watch where the move happens. Let's unpack this. A loop written as for task in tasks consumes the vector and moves each string out. That is useful when you're done with the collection, but here we still need tasks ln afterward. Now we fix the loop by iterating over tasks. Each task is borrowed for printing and the vector remains owned by main. Now we run it and the final count is still available. The best choice is simple. Borrow in the loop when you need the collection later. Use consuming iteration only when the collection is finished and you want to take ownership of each item. That one decision prevents many moved value errors. In this section, we look at ownership inside collections. The key idea is that reading from a vector is different from taking ownership of an element. Suppose we have a list of usernames and want to select the first one. A beginner may try to assign users directly into a new variable. Let's run this and see why indexing does not transfer ownership. Let's explain the important part. The vector owns every string, and moving one out by index would leave a hole in the vector. Rust avoids that hidden invalid state, so it asks us to borrow, clone, or remove explicitly. Now we fix the common read-only case by borrowing the first user. The vector still owns the string and selected just points to it for printing. Now we run it and can still use the vector afterward. The best practice is to choose the access pattern that matches your intent. Borrow when you only need to read, clone when you need a second owned copy, and use remove or swap remove when the item should leave the vector. That makes ownership transfer visible in the code. In this section, we look at a common collection mistake, keeping a reference into a vec while also trying to change the vec itself. In a message queue, it is tempting to grab the first message and then keep appending new messages. Here, we take a reference to messages, then we push another item, and now we run the code to see what Rust says. Let's break down the error. The reference first points inside the vector, but push is a structural mutation. If the vector grows and moves its buffer, that old reference could point to invalid memory, so Rust blocks the code at compile time. Now we fix it by storing the index instead of a reference. We mutate the vector first, then create the reference after the vector is done growing, and now the program runs normally. The best practice here is to avoid holding references into a collection while changing its shape. Use an index when you only need to find the item later, or clone a value when you really need independent ownership. Now we move to structs, where the key idea is to borrow the smallest part of the data that your code actually needs. Imagine a profile screen where we read the username and update the score. The helper function looks harmless, but it borrows the whole profile to return the name. Now we run it and see the borrow conflict. Let's unpack the problem. Rust can split borrows across different fields, but the helper function hides that detail by taking profile. The compiler must be conservative because the name reference is tied to the whole profile borrow. Now we make the borrowing explicit. We borrow name and score as separate fields, update the score, and then run the code again to confirm the profile is updated. The best practice is to design helpers around the data they really need. If a function only reads the name, pass profile.name or ASTR, not the entire profile. This section focuses on partial moves. Moving one owned field out of a struct can make the original struct unusable as a whole. In a user management feature, we may want to read an email and then log the full user. This code moves the email string out of the struct, then runs into trouble when we try to print the whole user. Let's break down the ownership change. The email field is a string, so assigning it to email transfers ownership out of user. The remaining fields still exist, but the original struct is no longer complete, so debug printing the whole thing is rejected. Now we fix it by borrowing the email instead of taking ownership. We only need to inspect the value, so a reference is enough, and the full user stays usable. The best practice is to borrow when you're only reading a field. Move a field out only when your next step is to consume or rebuild the struct intentionally. Pattern matching is expressive, but patterns can also move owned values if you do not match by reference. Here we have a status enum that stores an error message. We match on the result to print the message, then we try to print the enum again. Now we run it and see that the match pattern moved the string. Let's analyze the pattern, because we matched result by value. The MSG binding takes ownership of the string inside the enum. That is perfect when we want to consume the enum, but not when we only want to inspect it. Now we fix the match by borrowing the enum with result. The message is borrowed instead of moved, so after printing it, we can still print the final enum state. The best practice is to choose the match style based on intent. Match by value when you want to consume the enum, and match by reference when you just want to inspect what is inside. In a cache, we often want to check whether a token exists and then continue using the cache. This version uses if-let directly on the option field, so the token is moved out. Now we run it and look at the compiler error. Let's break down the pattern. Some token creates an owned binding, so the string inside the option is taken out. The cache still has its hits field, but the whole struct is no longer complete. Now we fix it with asRef, which turns option string into option string for this check. We print the token by reference, update the cache, and the final output shows the cache is still intact. The best practice is to borrow options when you're only checking or displaying their contents. Use as ref for read-only access, as mute when you need to modify the value inside, and move only when you truly want to consume it. In this section, we focus on lifetime relationships. The key idea is that Rust lifetimes do not make values live longer. They describe how borrows are connected. In real code, this comes up when a helper chooses between two borrowed values. Here we write a longest function that returns one of two string slices, and then we run it. The logic looks obvious to us, but the signature does not give Rust enough information. Let's break down the compiler message. The function may return X or Y, so Rust needs one named lifetime that connects both inputs to the output. The annotation will not keep either string alive longer. It only describes the allowed borrowing relationship. Now we fix the signature by adding one lifetime parameter. This says the return string slice is valid only for the lifetime that both input slices can safely share. Now we run the same program and the longer string is printed. The best approach is to use lifetimes only to describe real relationships between borrowed values. Apply them when a returned reference comes from an input reference. If the function can return either input, the output lifetime must be connected to both possible inputs. For a quick variation, make the second string longer and run the code again. The same lifetime signature should work because the relationship is the same even when the branch changes. Imagine a parser that keeps a long-lived source string but also logs a short temporary helper value. We accidentally reuse the parser lifetime for the helper parameter. Now we run it, and Rust complains because the temporary helper is forced into the wrong relationship. Let's unpack the problem. The parser source and the debug helper are separate borrows, but the signature says they must share the same lifetime. That makes the helper look like it must survive as long as the parsed word, even though the method only prints it. Now we fix the helper method by letting its parameter use its own short borrow. We do not need to name that lifetime, because Rust can infer it. Now the temporary helper ends inside the block, and the parsed word still prints afterward. The best pattern is to keep lifetimes independent unless the data really depends on the same borrow. Use the struct lifetime for data stored in the struct. Use elision or a separate lifetime for temporary arguments that are only used during the call. Try adding a second method that prints a temporary label. Keep that label independent from the parser source lifetime, because the parser does not store it. This happens when we create a lightweight view over existing configuration data. We want the struct to point at an application name, so we add a string slice field. Now we run it, and Rust immediately asks for the missing lifetime. Let's explain the error in plain terms. A config view value may be passed around, so Rust needs to know that its name reference cannot outlive the original app name string. The lifetime belongs on the struct type because the struct stores the borrow. Now we add a lifetime parameter to config view and apply it to the name field. This tells Rust that any config view is tied to the lifetime of the borrowed name. Now the program runs and prints the view name. The best choice depends on how long the struct should live. If the struct is a short view over existing data, a referenced field is fine. If the struct is long-lived or stored in many places, owning a string is often simpler. For practice, rewrite config view so it owns the name as a string. Then create it from app name time clone and notice that the struct no longer needs a lifetime parameter. Now we move to iterators. The important question is simple: does the iterator own the data, or does it borrow data that must stay alive somewhere else? Here we generate a small list of IDs inside a function. The mistake is returning IDs.iter, which borrows the local vector. Now we run it, and Rust prevents us from returning an iterator that points into data that is about to be dropped. Let's look at the ownership. The vector lives only inside generated IDs, and iter creates references into that vector. When the function returns, the vector is gone, so those references would be invalid. Now we fix the function by returning an owning iterator into iter. Takes ownership of the vector's values, so the iterator carries the IDs out safely. Now the run prints each generated ID. The best rule is simple. If the function creates the data, return owned data. That can be a vec, or it can be an owning iterator from into iter. Use iter only when the collection already lives outside the function. Try the vec returning version next. Store the vector in main, then call iter there, where the vector is still alive for the whole loop. The last section in this batch is about closures. Closures can borrow values, mutably borrow them, or move them, and that choice changes what the surrounding code can still use. This pattern appears when we build a delayed job and want it to remember a command. We use a move closure, so the closure owns the string. Now we run it, and the next println fails because command has already been moved. Let's make the ownership visible. String is not copied automatically, and move tells the closure to take ownership of captured values. After job is created, command no longer belongs to main. Now we fix it by cloning the command before the move. The closure owns command for job, while main keeps the original command for the immediate log. Now both messages print in the expected order. The best habit is to choose the closure capture mode on purpose. Use move when the closure must outlive the current scope or run elsewhere. If the closure only runs immediately, borrowing without move may be simpler. For practice, remove the move keyword and keep the immediate println before job is called. Then try moving job into another function and notice when ownership becomes necessary. In this section, we look at ownership inside closures, especially the moment a closure silently becomes one-shot because it consumes captured data. Imagine this: callback sends a string payload to an API, and we want to retry it. The closure looks reusable, but inside it moves the string into send. Now we run it, and the compiler points at the second call. Let's break down why this happens. A closure that moves captured data out of itself implements FN once, because after one call it no longer has everything it needs. Rust rejects the second call instead of letting us send missing data. Now we fix the callback so it can be called more than once. Instead of consuming the string, the closure borrows it and passes a string slice to send. Now we run it and both attempts succeed. The best practice here is to choose the closure trait based on the job. Use FN once for one-shot work, but for retries, design the closure so it borrows state or clones only the small piece it truly needs. Now we move to threads, where ownership becomes stricter, because a spawned thread can keep running after the current function returns. In a real worker system, we might spawn a thread and print the job name it is handling. This version borrows the local string from the main function. Now we run it, and Rust refuses, because the new thread needs data that can outlive this stack frame. Let's unpack the error. The main function owns job, but the spawned thread might run after main has moved on. Rust therefore asks for a closure that owns its captured data, not one that borrows from the current stack. Now we add move to transfer ownership of the job name into the thread. The worker owns the string, so there is no borrowed stack data left behind. Now we run it and the thread prints the job name. The best practice for spawned threads is to use move deliberately. Give the worker ownership of only the values it needs, so the thread is independent and the lifetime rules stay simple. Let's increment one shared counter from several worker threads. The mutex protects the number, but this code tries to move the same mutex into every closure. Now we run it, and Rust catches the ownership problem before any thread starts. The important detail is that mutex handles synchronized access, not shared ownership. The first spawned closure takes ownership of the mutex, so the next loop iteration has nothing left to move. We need a thread-safe reference-counted owner around the mutex. Now we fix it with arc-mutex32. Each thread gets its own cloned arc, but all of those arcs point to the same mutex. Now we run it and the final counter shows that every worker incremented the shared value. The best practice is to separate the two jobs clearly. Use arc when several threads need to own the same value, and use mutex when that shared value must be changed safely. This section shows a different kind of ownership mistake, code that compiles, but breaks borrowing rules at runtime through interior mutability. A common use for refcell is a test logger that records messages through shared access. This code takes one mutable borrow, writes a log, and then asks for another mutable borrow while the first guard is still alive. Now we run it, and this time the failure happens at runtime. Let's break down the panic. Refcell still enforces the rule that only one mutable borrow can exist at a time. The difference is that it checks the rule while the program is running. Now we fix it by making each mutable borrow live in its own small block. The first guard is dropped before the second borrow starts. Now we run it and both messages are stored. The best practice with refcell is to keep borrow guards tiny. Take the borrow, do the work, and let the guard drop before the next operation that might borrow again. Finally, we look at a design trap that feels natural at first, but fights Rust's ownership model: ordinary self-referential structs. This shows up when parsing text. We want to own the full buffer and keep a slice for the interesting part. The struct stores a string and its target that points into it. Now we run it, and Rust rejects the self-reference. The problem is not the slice itself. The problem is storing a reference into data owned by the same struct. If the struct moves, Rust would need to keep that internal reference valid, and ordinary structs do not provide that guarantee. Now we change the design. The struct owns the string and stores a byte range, not a reference. When code needs the slice, we compute it from self, then run the program and get the expected text. The best practice is to avoid self-referential structs while learning Rust. Store own data with indices, ranges, or IDs, and create short-lived references only inside methods. Reach for specialized crates only when this pattern is truly necessary. Now you have seen the most common Rust ownership mistakes and how to fix them. If this helped you understand the borrow checker better, like the video, subscribe to Dev Level Up, and write in the comments which Rust topic you want next.